Section 3.7, Rates of Change in the Natural and Social Sciences. Today in class we covered a physics example, so now I'm going to start on a biology example. These are really just applications of future things that we have already, previous things we have already covered. Let n equal f of t be the number of individuals in an animal or plant population at t. So the change in this population at times t1 and t2 is going to be represented by the change in n of f of t minus, f of t2 minus f of t1. So the average rate of growth can be represented by this formula below that we have previously covered in chapters 2.7 and 2.8, I think, and also earlier in this PowerPoint. The instantaneous rate of growth is obtained from the average rate of growth by letting the time period change in t approach 0. And this can be found by using the limit as change in n over change in t. So this is not 100% accurate because the actual growth of the population is n equals f of t, which would technically be a step function, which is discontinuous. However, we can represent it with a smooth approximating curve, as you can see in the following picture. So there's the step function, but we can approximate it with this smooth curve. So to be more specific, consider a population of bacteria in a homogeneous nutrient medium. Suppose that by sampling the population at certain intervals, it is determined that the population doubles every hour. So f of 1 is 2 times f of 0 equals 2. F of 2, 2 times f of 1, so on and so forth, 2 squared, 2 cubed. So in general, f of t equals 2 to the t n naught. Or n0 is the initial population, however you want to call it. The population function is n equals n naught 2 to the t. In section 3.4, we showed that the derivative of a to the x equals a to the x ln a. So the rate of growth for the bacteria population at time t is going to be 0.2t ln 2. For example, suppose that we start an initial population of 100. Therefore, we can just take 100, plug it in for n naught, and we get 100 times 2 to the 4. Why? 2 to the 4, because of 4 hours, equals 1600 ln 2, which approximately equals 1109. That means after 4 hours, the bacteria population is at a growing rate of about 1109 per hour. So all we did in this biology example was find a derivative of something they gave us using a formula we had already covered in 3.4, and then plugged in the information from the problem into this derivative as we have done in previous chapters. So what about economics? So suppose C of x is the total cost that a company incurs in producing x units of a certain commodity. The function C is called a cost function. This can be found right here, where the number of items produced is increased from x1 to x2 and the additional cost, change in cost, equals cx2 minus x1, and the average rate of change is as shown below from applying a previous formula. The limit of this quantity as change in x approaches 0, that is, the instantaneous rate of change of cost with respect to the number of items produced, is called the marginal cost by economists. The marginal cost equals, limit is change in x approaches 0, change in c over change of x, derivative respect to c, derivative respect to x. Now, taking change of x equals 1 and n large, so that change of x is small compared to n, we have this as follows. Thus, the marginal cost of producing n units is approximately equal to the cost of producing one more unit. It is often appropriate to represent a total cost function by a polynomial. So here, a represents the overhead cost, whatever it would be, and the other terms represent the cost of raw material, labor, so on and so forth. So another way to think about it is your bill. So this would be my rent of my house, and then my utility that changes, my, cable bill, my gas bill, all those things seem to change every month. So the cost of the raw materials may be proportional to X, but the labor costs are going to depend partly on the higher powers of X because of the overtime costs, insufficiencies involved in the large-scale operation. So like I said, with my rent is going to stay the same every month, but things are going to change as in my power with the energies outside. Of course, my time, water, cable bill is going to go up because they decided to do that automatically with no talking. And D, of course, our gas bill can go up and go down depending on if we use it for heat or the stove or other things in life. So now, for instance, suppose a company has estimated the cost in dollars of producing X items is this, where the marginal cost of the function is this, which is simply just the derivative of the estimated cost up there. The marginal cost at the production level of 500 items is as so. All we do is take 500 and plug it in for X, and we get $15 per item. So this gives us the rate at which the costs are increasing with respect to the production level. When X equals 500, this predicts the cost of each item, the 501st item. The actual cost of producing the 501st item is $15.01. So notice that derivative of 500 is relatively similar to 501 minus 500. And that's it. In general, the second derivative can be interpreted as the rate of change of a rate of change. The most familiar second derivative is acceleration, which is the derivative of velocity or the instantaneous rate of change of velocity with respect to time, like in the physics example we covered previously. All right, now practice WebAssign.